Good morning, everyone. Welcome to Nano Open Webinar. We have Dr. Barun Chakrabarti, one of new researcher of the SUNUM Family today. He will talk about application of carbon-based nanomaterials as elektrot catalyst for redox flow batteries. Nowadays, redox flow batteries are one of the most promising solution for large-scale energy storage system due to such advantages as long lifetime, safety, the ability of deep discharge, and flexibility of energy and power ratings. Dr. Barun, welcome to SUNUM again. The stage is yours. Would you introduce yourself to us while starting the webinar?
Okay, I'll first start sharing the screen and then continue. Yes. Okay. So I've been working on nanomaterials for redox flow batteries for a long time, let's say 10 years, maybe even longer. And mainly in Imperial College, and then I took this research into WMG, where I was last working. And the reason I'm choosing redox flow batteries is my PhD subject. This is what I did in my University of Manchester, and I've tried to always continue doing this work all throughout my career. So today's talk will be kind of my journey with redox flow batteries and nanotechnology in a way. So continuing with the presentation, so I think some people may know what flow batteries are, and as Dr. Hanım explained, one of the key attributes of this technology is the ability to decouple power and energy. So you can optimize the capacity of the electrolytes separately from that of the power converting unit, because your electrolytes can be stored separately in separate tanks and not within the battery container. Some generic reactions are given here, like charge and discharge and so on, like A and B, but basically any kind of redox chemistry can apply. Anything which can give you a reasonable voltage when coupled together can work. So some examples, so I'm going to move from showing what the concept is, then I'm going to give you some examples of some commercial systems. These are photos of like companies that are actually selling products, and this is not like your like a phone battery or power or Tesla Powerwall or something. This is much bigger, and you can see the size of some flow batteries this is like the entire, with the battery management system and everything in there, with many stacks in there, and it's bigger than a human. So some of them can be like a bunker, like you can like a size of somebody can stay in this kind of a system for, I mean, in this kind of size of a room, for instance. So it's pretty big, and these are at the TRL level 9, and they are being sold like this is all vanadium flow battery being sold in China as well as in America. ESS is a popular one for selling the all iron hybrid flow battery, and the reason I'm saying hybrid is because it's no longer a liquid system. There's one side of the chemistry involves deposition of iron iron metal. So then, because you have the solid deposition, is no longer a fully soluble flow battery. Similarly, for the zinc bromine system is also another system which is hybrid, because the zinc system requires deposition of the zinc metal in one of the half cells. And the other system which is being sold in US is iron chromium, which is the original system that was patented by NASA and applied by them, but it wasn't very successful. So the thing is, people normally when you say batteries, people normally think about the phone battery, like lithium-ion batteries, which is the most common system that comes to mind. But nobody seems to know much about, or maybe very few people will know okay, I've yesterday I was walking with my friend and I saw a flow battery plant, and yeah, man, it's so big and something. No, people don't talk like this. And the reason for this is like in our community of flow battery, when we go to seminars and so on, we have, and when I was at Imperial, we used to have some visitors coming from Canada and so on. So one of the visitors for working on flow batteries, he said that we don't have an Elon Musk to actually champion our technology. So not many people know about flow batteries as much as lithium-ion batteries. And the other problem with flow batteries is the reason why it's not widespreadly available is because the cost of energy storage doesn't meet the DOE standard as yet. And the reason I put space redox in case is because this is the original iron chromium flow battery, which was developed by NASA in the late 1970s. And they actually used this in spacecraft missions for storing energy. But then it wasn't really successful. So other kinds of flow chemistries came about, for instance, all vanadium flow battery and so on. Here is the ESS Inc. In America. They are using this technology of the iron hybrid flow battery. So like I was saying, you have iron deposition on the anode. So it's a hybrid system. It's not fully liquid. And on the other side, you have the iron 2 and iron 3 chemistry. Because the components are quite cheap, so it's possible to scale up. However, it has its own problems, and that's one of the reasons why it's not as well known as lithium-ion batteries. Other chemistries are shown here, like the all vanadium flow battery. This is the standard one, first time patented in late 1980s. It's being as soon as anyone hears about flow batteries, the first thing that comes to mind is a vanadium flow battery. Other chemistries like iron chromium, the one that NASA first introduced, the chemistries are shown here. So now I'm going to go a bit from TRL level 9 to TRL level 7. So the polysulfide bromine flow battery, this was being developed in the early 2000s. So this is my PhD supervisor from University of Manchester, now in University of Calgary, Canada, and along with him was my when I was finishing my PhD, Professor Frank Walsh. He was my PhD external examiner. So these two were in those times in the early 2000s were considered to be the gurus of electrochemical engineering. So they were developing this polysulfide bromine system, and they were trying to fit this into develop a company along with this Regenesis in those times, and they were almost commissioning a plant in Little Barford in south of Wales. However, due to the company being taken over by another company, foreign company, they changed the idea and they didn't want to continue with this. So this technology didn't actually get commercialized in the end. However, a Dutch company from University of Eindhoven startup, they took the idea of the bromine, they removed, they said we won't work on the polysulfide, we look at the bromine side, and we will combine with the hydrogen redox couple, hydrogen proton redox couple, and then we will come up with a very low cost system, and they are doing pretty well at the moment. However, the large size commercial systems are still not available. They're still working towards it. However, the cost of storage is coming down, which is good. So hopefully in future we'll see some technologies coming out from them. On a parallel scale level, my own supervisor when I was doing postdoc for 7 years in Imperial College, Nigel Brandon, he looked at the polysulfide side. He said the bromine is an unsafe compound, so if it can be toxic, so rather use polysulfide and combine it with the oxygen from the air, and they come up with a relatively cheap system which can work. And so this is being he has patented this technology with my colleagues in Imperial College, and they are trying to make this system work. However, those who work with lithium sulfur batteries know how troublesome the sulfide polysulfide chemistry is. So it's not so easy to scale this up. So while he's working on this, he's also looking at all manganese chemistry. because manganese is another ubiquitous metal which is quite cheap. So he's trying to replace the vanadium system. So looking at the manganese chemistry, which was developed by Sumitomo in Japan and EPFL in Switzerland, they face problems of during charging of the manganese, you have irreversible manganese dioxide formation. So one of the patents which parallelly developed by Sumitomo as well as at Imperial College by one of my colleagues, they added titanium salts, and that managed to suppress the manganese dioxide formation and can avoid capacity fade. So this is the main system, hydrogen manganese system, which Nigel Brandon is working on in Imperial College with his spin-off company, RFC Power. So while they're doing this, they're also trying to work on the polysulfide air flow chemistry, which I mentioned before. And then moving a bit lower to TRL level 6, then there's the all-soluble lead acid flow battery as well, which my previous supervisor in WMG was working with Frank Walsh in the past. So these are the technologies which are kind of scaling up, but there are still a lot of problems with this system, which doesn't allow widespread exploitation. And one of the issues is to do with electrodes. So this is where my research comes in. I'm working on improving the electrodes so that the systems, let's say the power densities can be improved, so you can have less cells in a stack, so you can reduce the cost, and you can try to improve the commercial availability, commercial reach out. So here there are 3 different types of research that I've been trying to do, mainly based on electrophoretic deposition, which is a technology we developed in parallel with Imperial College as well as with WMG, and electrospinning, and then using these graphene and CNT modified electrodes for different kinds of flow batteries. So we started with hydrogen vanadium flow batteries, but I will come to that. So focusing on the graphene modified electrodes. So the question comes in, why modify the electrodes? Because there are so many electrolyte systems and so on. So what is the role of the electrodes here? The electrodes, as I mentioned before, I probably mentioned that they used in from a micro scale, if they are not able to perform proper charge transfer at the surface, then the kinetics of the system is poor. The power densities goes down, the energy capacity goes down, and your system stacks become more cumbersome. You have to have more cells, and becomes more expensive. So what is done in the literature normally, they do a very long, extended heat treatment process to try and make the standard carbon-based electrodes hydrophilic. Here's a X-ray tomographic imaging of how a carbon-based electrode behaves when it first comes into contact with the vanadium electrolyte. So in the beginning, vanadium starts infiltrating. So this is without any treatment at all. This is just the carbon electrode, carbon paper, or carbon felt as it is. And you can see that electrolytes are going in, but not going through the entire volume. It's going through selective pockets. After several hours, it's still not fully wet. And then maybe 6 hours to 8 hours is still not fully wet, but you can see the vanadium is kind of going more or less in various parts of the carbon. So heat treatment reduces this low coverage of the electrolytes on the electrodes, but it's still very long process. It's also thermal treatment, like let's say 500 degrees or 700 degrees in the furnace. This costs money. And an alternative to that, let's say, is plasma treatment. That also it's possible. It can also do the same trick as a heat treatment, which allows instantaneous coverage of the electrode surface by the electrolytes. However, if plasma treatment loses its effectiveness if you leave it in air for 1 hour or so. So we thought in Imperial College, and along with our collaborators in WMG at that time. This is around 2015-16. So this is before I moved to WMG. I'm still at Imperial College at that time. So we thought, why don't we find a different way to modify the electrode surfaces with some nanomaterials? And first nanomaterial that came to mind was graphene, because graphene was very popular at that time. So we thought, okay, let's get some commercialized reduced graphene oxide, and let's try to deposit that on the surface of a commercially available carbon paper electrode and see how that goes. So using the idea of my at that time collaborator and later on my supervisor WMG of depositing NMC on aluminum foil by electrophoretic deposition, we thought let's try to make rethink this idea. Let's turn this standard vertical electrophoretic deposition reactor into a horizontal one, meaning we put this working electrode on the top and the counter electrode at the bottom. So you have this system here. This is where the working electrode will fit, which is here, and there's a spacer in between, and the counter electrode is at the bottom. And then let's see if we can try to deposit some reduced graphene oxide on the carbon paper and see how that works. And the idea is because graphene agglomerates in solution if you leave it without sonication. So we are trying to use electric voltage to try and push the few layer graphenes onto the carbon paper on top, whereas the cumbersome graphitic particles that form from agglomeration of graphene can fall to the bottom by action of gravity. So we are kind of selectively trying to get the few layer graphenes to stick onto the surface of carbon paper. So after a year or so of experiments, along with some students, we managed to deposit on both sides as well as one side of the carbon paper. And from the Raman analysis, we could see that after deposition of reduced graphene oxide, from crystalline structure, it was becoming more amorphous. So we could say that yes, there is reduced graphene oxide from Raman spectra. Then we tried to do electrochemical testing on using a 3-electrode cell, still not in a redox flow battery. We did cyclic voltammetry to show that even though it's not very clear, we can just about see that the kinetics of the reduced graphene oxide modified carbon paper is better than that of the original carbon paper, untreated carbon paper. And this is a reconstructed X-ray tomographic image of reduced graphene oxide deposited and filling in the pores of the carbon paper. So we did impedance analysis, and then we showed that when you deposit reduced graphene oxide on only one side of the carbon paper, you get the lowest charge transfer resistance. So then the question comes, what is this no RGO here? So this is something which Nigel Brandon, when I took these results to him, he said that, how do you know that it's the reduced graphene oxide which is improving the performance? It could be that the DMF, in which the reduced graphene oxide is RGO is suspended in, maybe modifying the carbon paper surface and maybe giving some sort of surface functional groups, which is improving the performance. So try a control experiment, do the same kind of electrophoresis as with the reduced graphene oxide, but without the nanomaterials, and see how that performs. So we did that. We used the same voltage and same parameters, and we saw that there is minor improvement. The charge transfer resistance does improve, but not so much. And if we do have the nanomaterials, reduced graphene oxide, performance is much better. Then we did testing of a non-aqueous vanadium flow cell. In this case, we looked into literature and saw that reduced graphene oxide works well, but nitrogen doped graphene is better. It improves the conductivity of the electrodes even more. So let's see how that performs in a non-aqueous vanadium flow cell, which I was developing when I was in Malaysia around 2010 to 2012. So I was working with ionic liquid analogs known as deep eutectic solvents, and we were trying to make these new electrolytes work in all vanadium flow batteries. So I thought, why not combine what I'm doing at Imperial College and WMG of depositing electrophoretically nitrogen doped graphene. So here, what we see here is the carbon paper, which I showed earlier, on its own without any modification. It has some graphitic structures on one node, like one fiber. The same fiber, after a nitrogen doped graphene deposited on it by electrophoretically, you can see several layers on few layer graphene and so on deposited on the node. And this is a TEM image of nitrogen doped graphene. And this is an X-ray tomography radiographic image of these nodes, like these fibers. You can see them here, and you can see also some reduced graphene, nitrogen doped graphene around the surfaces. And when the X-ray tomography image is reconstructed, you can see the blue particles are the nitrogen doped graphene, and these green are the carbon paper fibers. So the electrophoresis reactor is here. You can see the horizontal deposition process by applying around 300 volts of voltage without any current. We were able to move the reduced graphene oxide few layers up into the working electrode surface here, and then whatever was agglomerated heavy graphitic particles were falling at the bottom. So we could have some decent depositions, and we compared the nitrogen doped graphene with a standard carbon paper with cyclic voltammetry, and we showed that the performance is much better when we have nitrogen doped graphene deposited onto the carbon paper. So here we are not using any binders, so it's quite an elegant process, and works quite effectively. The ionic liquid here is a standard system from which was reported in the literature. So we are just trying to compare and see how our electrolyte works with the ionic liquid. So after doing the cyclic voltammetry showing good performance, we then assembled a homemade flow cell in Imperial College, and then we obtained some energy efficient charge and discharge performance. So this is showing charge and discharge energy efficiencies after 5 cycles. So you can see that there are different current densities. We are getting reasonable energy efficiencies when the nitrogen doped graphene, or NGCP, is deposited onto the carbon paper. But because this is a non-aqueous system, we were not able to extract much higher current densities. Still, for this system, it has been doing for quite well. Then we did cycling for up to 20 cycles. Energy efficiency of the standard carbon paper was dropping, whereas that of the nitrogen doped carbon paper seems to be more steady. And another important figure of merit for redox flow batteries, which is the electrolyte capacity utilization, especially during discharge, is also showing that the nitrogen doped graphene deposited electrophoretically is performing better than the standard carbon paper. This graph I put over here because traditionally non-aqueous vanadium flow cell or any other flow non-aqueous systems like manganese or ruthenium or so on, they always use acetonitrile as the solvent. And acetonitrile is both flammable as well as toxic, and also quite expensive. So here I'm trying to, in this graph, in this paper that I published, I was trying to convince the other researchers that try to use ionic liquids or something analogs, which are cheaper, and some of these materials are also available naturally. Like for instance, ethylene glycol or urea or choline chloride, which is used for chicken feed. So it will be better to replace acetonitrile. So in summary, so I did electrophoretic deposition of reduced graphene oxide and nitrogen doped graphene, tested them in an aqueous flow all vanadium flow battery, which is a standard system in the flow battery literature. And we found good performance for both aqueous as well as non-aqueous systems. The aqueous system uses sulfuric acid as well as vanadium sulfate dissolved in it. The non-aqueous system is using vanadium acetonate, a ligand-based system, vanadium system, complex system dissolved in the ionic liquid or the deep electric solvent. Now moving on, we also tested at Imperial College these carbon felt modified electrodes with reduced graphene oxide in a hybrid hydrogen vanadium flow battery. Again, hybrid because this is not a liquid, this is a gas. So the hydrogen proton transfer reaction. So it's still being called a hybrid system. So we tested the reduced graphene oxide, and what we found is that we compared that with standard heat treatment procedures for the carbon paper, and we found that the reduced graphene oxide performance, power densities is almost the same as that when we do heat treatment, and also depositing reduced graphene oxide on a heat treated carbon paper. Cycling here, there's a wrong label here. This is actually untreated, means reduced graphene oxide deposited onto the carbon paper. So the black. So we did up to 10 cycles. Energy efficiencies are almost the same as if we do heat treatment as well as depositing reduced graphene oxide on it. And the standard heat treatment of the carbon paper without depositing nanomaterials is not as good as the depositing reduced graphene oxide. That's for energy efficiencies. And again, discharge capacity utilization, you can see that depositing reduced graphene oxide onto the carbon paper is performing better than heat treatment. And doing electrophoresis, you can have your carbon paper ready, or your electrodes ready within a few hours, or even less than a few hours, maybe like 2 hours if you have the electrode. Whereas this heat treatment takes 72 hours to get this much performance. So we are showing that we can reduce costs and you can get better performance. So this was the hydrogen vanadium flow battery. So then we also tested 3 different systems, 3 different hybrid flow cells or regenerative fuel cells. The hydrogen vanadium, again, hydrogen manganese, and the polysulfide air, which I described earlier. We were doing in Imperial College. Nigel Brandon is trying to commercialize this system, so we also looked into this as well. So again, this cartoon here shows the this is the horizontal electrophoretic deposition reactor. You have the nanomaterials depositing on the top, and then especially nitrogen doped graphene being applied to 3 different systems. The main results are as follows. So we did morphological analysis of the deposited carbon papers. This is nitrogen doped graphene deposited on standard commercially available carbon paper, different resolutions. You can see the flake density is very high, and if you do, this is a TEM image, both of the TEM images of the nitrogen doped graphene, and here are the XPS results. And then the XPS of the nitrogen doped graphene shows that there are 4 different nitrogenous species, and the one from the literature that affects the vanadium reaction is the graphitic one. Well, this actually improves the performance of the vanadium charge transfer reaction. Also, the BET surface area is much higher for the nitrogen doped graphene compared to reduced graphene oxide, or the pristine SGL is the name of the company that sells this carbon paper. And the Raman spectra also shows more amorphous behaviors of the nitrogen doped graphene compared to the original unmodified carbon paper. The results in a hydrogen vanadium flow cell. So we did some comparison at different cycles and different applying different current densities, almost like as done in the standard battery testing. So we showed that the energy density for nitrogen doped graphene is quite good, and it recovers after 200 milliamp per centimeter square. You go back to 50 milliamp per centimeter square, you can almost get the same energy capacity. Then we compared the energy efficiencies, cycling energy efficiencies after 5 cycles for 4 different current densities, and again the nitrogen doped graphene is doing much better than the reduced graphene oxide modified or the standard carbon paper. Specific capacity is also better for nitrogen doped graphene. Peak power density is also good, however, is not the best, so it still requires further research. And after 150 cycles, the energy efficiency is reasonably stable, although there are some drops, and the capacity utilization is also not too bad. Then, after getting reasonable results with the hydrogen vanadium, we tested the hydrogen manganese fuel cells, which is also being commercialized by RFC Power. So we wanted to see how that performs, and can we feed in some useful knowledge from the nitrogen doped graphene for the company to take further. So again, as for the vanadium system, the hydrogen manganese system is performing better when we have reduced graphene oxide, nitrogen doped graphene deposited onto the carbon paper electrodes. One thing I forgot to mention here is that we are only modifying the liquid side chemistry. We're not modifying the hydrogen proton reaction here. So the hydrogen proton reaction carbon paper is a standard one which is obtained commercially from Alpha ESAF. It has some standard loading of platinum on it. So we didn't play with that. We only modified the vanadium and the manganese side chemistry of the electrodes, and we were obtaining good performances. This power density here is as good as the standard system that was reported by our colleagues who, when they first patented this technology in 2018, they got similar power densities using graphite felt electrodes. And graphite felt is one of the most commonly used electrodes in flow battery literature because of high surface area and so on. So here we are actually getting almost the same performance with much thinner electrodes and with after modification with the nitrogen doped graphene. So again, just like the vanadium system, we are showing this energy efficiencies are good. We can only do up to 50 cycles at that time, and the discharge capacity utilization is also not bad, and is much better for nitrogen doped graphene compared to the pristine carbon paper without any modifications. Then we decided to test the polysulfide air chemistry. However, polysulfide chemistry is not easy, it's very difficult to work with. So initially we just did some linear sweep voltammetry and compared the TAFL slopes for the modified electrodes against the standard commercially available carbon paper. And we found a slightly different result here. We found that the reduced graphene oxide was giving better performance in polysulfide chemistry than the nitrogen doped graphene. And we postulated that the polysulfide chemistry seems to be performing better if there is oxygenated functional groups present instead of nitrogenous groups. So when we actually assembled a flow battery, and this is around 2020, 3 years ago, and we did polarization and power density curves, we actually managed to see, again, similar to this 3 electrode system, we managed to see for the flow battery a higher power density for reduced graphene oxide modified carbon paper. However, as you can see, the power densities are very low, and this is again because of the complexity of the polysulfide chemistries and its interaction with the carbon-based electrodes. So we also did some preliminary costing analysis to show standard all vanadium flow battery, which is very common in the flow battery literature, and we compare that with the hydrogen vanadium flow battery, hydrogen manganese flow battery, and the polysulfide air. And as you can see, for different power densities, the polysulfide air gives lower cost. And if its power densities can be improved in the future, then it is likely to do very well. The other technique that I tried afterwards, after electrophoresis, is electrospinning to prepare self-standing carbonized mats. After electrospinning, we also did carbonization at 850 degrees C, and then using the specific like iron acetylacetonate precursors, we were able to grow some encapsulated carbon nanotubes on like with some hairy structures, which our colleagues call trichomes, and this is like a cartoon version of this carbon nanotubes grown on the trichome-like structures. So this was roughly, I think it was 100 micron thick self-standing electrodes. This here shows the procedure in time, how using polyacrylonitrile as and iron like 30 to 48% of iron compared to the pan, and then after that carbonization, and you can see how the carbonized structures form, the hairy structure, the trichome-like structures form after carbonization. This is a SEM of commercially available carbon cloth electrode, which has been reported to do very well in the flow battery literature by a flow battery group in MIT. So we were collaborating with MIT in the 2020s, like 3 years ago, and then they suggested us to use this particular electrode and test that in our systems. So we did some charge and discharge of this, as well as these trichome-like electrodes, the self-standing free electrospun electrodes, and then so the results are shown here. The electrolyte utilization after 150 cycles. So after 150 cycles, we did X-ray tomography. This is the self-standing carbonized metal fibers or the electrospun materials after 150 cycles, and you can just about see some of the the trichomes are still present. It's not fully it hasn't fully disintegrated. Whereas this is that of the carbon commercially available carbon cloth electrodes. So the blue is indicating the presence of the iron particles. So after 150 cycles, there is some amount of iron metal particles has actually gone into the carbon cloth electrode as well. What I didn't mention here is, if you look carefully here, we didn't use the carbon metal fiber electrodes on their own because they were quite fragile, and when we compressed them in the flow battery on its own, whether one single layer or three layers or 5 layers, after like few cycles they were crumbling apart. So we had to then use this ELAT, which is ELAT is the commercial name of this carbon cloth. We had to sandwich that along with the membrane, and then we could do this flow battery experiments. So here are some of the electrochemical results. Here shows the power densities for 3 or 4 carbon metal fabrics, the electrospun fibers on their own are sandwiched together, and you can see that the power densities are not great. But if one carbon metal fiber is combined with the carbon cloth electrode obtained commercially, we can get markedly improved performance. We get almost 700 milliwatt per centimeter squared power densities. This same CMF ELAT and compared with the carbon cloth gives much better kinetic performance with cyclic voltammetry than just the cloth on its own, commercial cloth on its own, and it can also be seen in the lower charge transfer resistance when the electrospun fiber mat is attached with the carbon cloth electrodes. Again, cycling performance after 5 cycles, we did up to 500 milliamp per centimeter squared, so we could obtain much higher current densities. Again, you can see that is when we have the electrospun mat along with the carbon cloth electrodes, the energy efficiency is very good. And we could also perform 500 cycles with this combination of carbon cloth and the CMF, which is the carbon metal fiber, or the electrospun carbonized metal fiber, and we could obtain very by 500 cycles is pretty good. And if we can improve this in the future, the making of the CMF, if we can make self-standing electrodes, and we could even try to go for longer cycles, and this can be something for long duration energy storage. And one of the reasons why the performance of this CMF ELAT is better than just ELAT is because you can see that we did cyclic voltammetry in just sulfuric acid here, and it's not showing it. This the component G, and we could show that the electrochemical surface area is better when the carbonized metal fiber is combined with the commercial ELAT cloth. The component for H here, this is a different experiment. We just use the CMF and the ELAT the carbon cloth and the carbon fiber together, and then for the first time we used a system where we recycled, because what we have is a hydrogen vanadium flow cell. Usually you have vanadium going through the membrane into the hydrogen side half cell, and you have to collect the vanadium electrolytes over there. So over time, your concentration of the vanadium increases, and you have a variation of performance. So no one before these experiments tried to collect that liquid from the hydrogen side half cell and pump it back into the vanadium electrolyte. So in this system, this is what we did. That's what with recycle means. We collected the crossover liquid and put it back into injected it back into the vanadium side again, and then with the recycling performance, we saw that the energy efficiencies are of this few percentage better. Then we also did some costing analysis of potential scaling up of this hydrogen vanadium system using the carbonized metal fiber for electrospinning material. These are actually for the same current density. This is actually a bit misleading. This is for 100 milliamp per centimeter square current density. This is 150 milliamp per centimeter square, and that's 200 milliamp per centimeter square. So this is just the carbon cloth on its own, commercially available, and this is the carbon cloth along with the carbonized metal fiber electrode attached to it. And you can see that the cost goes down. A more detailed analysis is shown over here. So for different durations of energy storage, you can see that the cost goes down. This is for 3 different current densities. And then we also did a preliminary analysis of how this system would perform, the hydrogen vanadium system with the carbon metal fabric. And if we do a system integration for grid level of electricity, load leveling, as well as renewable energy storage, as well as for water desalination plant and so on. And then after that, we then tested the hydrogen manganese fuel cell, which is currently being commercialized by RFC Power, and we wanted to see how this new electrospun material that we made can perform in these systems, hydrogen manganese systems. So the flow battery cell reactor is shown here, single cell. Initially, experiments were performed with 3 carbon paper electrodes obtained commercially. The results are being shown here for 3 different concentrations of the manganese. So this was mainly to determine the optimized electrolyte composition for the manganese, and we found that 1 molar is the best. So we used that. for testing the electrodes. So one single carbon paper compared to 3 carbon papers, you can see that 3 carbon papers are giving better capacities. And if you just use a commercially available felt after heat treatment, the 72 hours heat treatment, you can get better performance. But if you just use the felt without any heat treatment, and you put this our electrospun material next along with it in the same reactor, then you can see like very impressive performance compared to just the normal felt. Same thing you can see with the power densities. We are getting almost 600 milliwatt per centimeter squared when we're combining this green is the felt plus CMF. So these are all preliminary results that we obtained, and we hope to in the future do similar experiments with more improved carbon metal fiber electrodes, and if we can have self-standing electrodes without being supported by the commercial ones. Anyway, so here is just showing how the standard graphite felt modified with the carbon metal fiber performs at 3 different current densities, which is very commonly tested in flow batteries literatures. And also cycling. This is one of the few reports of hydrogen manganese flow cells being cycled 100 times or more using nanomaterials. So using these nanomaterials, I'm saying because carbon metal fiber has carbon nanotubes on the trichome-like structures. So modifying that, we have energy efficiencies above 80%, which is beyond the commercially acceptable level for standard flow batteries. So this combination of felt, standard felt with our homemade carbon metal fiber is showing promise, and maybe if more durable performances can be withstood by the system, then maybe it can be commercialized as well. So now coming to the end of this talk, my main focus has been on the electrode side, because the electrodes are usually, the standard electrodes are carbon based, and they are usually hydrophobic, and they add to the cost of a flow battery because of lower electrochemical surface areas for charge transfer reactions. And if you use standard procedures for improving this electrochemical surface area, such as thermal or plasma or acid treatment, chemical treatments, they are quite time consuming and increases the cost. So we have shown in our research that we can obtain equivalent, or if not better, performances if we modify the standard carbon papers, commercially available carbon papers or carbon felts with electrophoretic deposition, or if you make a self-standing electrospinning carbonized structure, which can be applied along with a commercial electrode and gives much better performance than standard carbon electrodes. So with this, I thank you for putting up with my presentation, and the future, what I believe, is working with green hydrogen. So if it's possible in the future that I can work with, collaborate with the researchers who can produce hydrogen from electrolysis of water or some other green method, then it can be fed into the hydrogen vanadium, hydrogen manganese flow battery systems. So thank you very much for your attention.
Thank you for your presentation, Dr. Barun. And now session is open for questions. You can just speak up or raise hand, or if you like, write on the chat box.
I want to ask one question.
Please, hocam.
Mr. Barun, you prefer to use some ionic liquids as a nitrogen source instead of polyacrylonitrile. What was the criteria that you looked at when you choosing the right ionic liquids? How did you decide which one to use? Did you check their viscosities, densities? What kind of selection did you follow?
For this ionic liquid, I didn't mention the name of it. It was being used in dye-sensitized solar cells, and it also had a reasonably good redox performance. So this was selected by my colleague for evaluation in the flow battery. However, the criteria that I was selecting for my deep electric solvents is low cost because of what do you call ubiquitous material availability. For example, I'm using choline chloride and ethylene glycol and forming a eutectic mixture out of that. And choline chloride is available for commercially as chicken feed, and ethylene glycol is used as antifreeze. So these are cheap materials. So you can just put them together and make a deep electric solvents. And as you rightly asked, one of the key criteria for which is also viscosity. So the viscosity of these ionic liquids are actually more than water. So it kind of impacts upon the performance of the system as well.
Yeah.
This is one of the reasons why a lot of non-aqueous flow battery experiments, they use acetonitrile because the viscosity is quite close to that of water. But the thing is, if someone is willing to compromise on the cost and heat up this deep electric solvent, let's say 100 degrees, then it's very safe, and it will give as good performance as acetonitrile, or even better. It might even come close to the aqueous systems.
Have you tried blending these ionic liquids with acetonitrile to make it cheaper, but the performance may increase with the addition of acetonitrile? Are they imidazolium type ionic liquids?
This one is imidazolium, the blue one. The other one is deep electric solvent, so it doesn't have imidazolium in it.
Okay.
However, yes, what you're suggesting, I've actually done that for graphene exfoliation. I've actually blended acetonitrile with several different deep electric solvents, and then try to do electrochemical graphene exfoliation. And then I don't remember which one I choose. I think it was the same D as the same one, ethylene glycol one, which was working the best. And one of the reasons is because this ethylene glycol one, known as ethylene, it has one of the lowest viscosities of the deep electric solvent family.
Yeah. How about the nitrogen content? Is there any relation with the nitrogen content? Because you also mentioned urea.
Okay. Yes, I didn't use urea. However, nitrogen content seems to, especially when you do nitrogen doping of the graphene, it seems to improve the conductivity of the electrodes, because I think there's a lone pair of electrons which is available from the nitrogen doped graphene, and it helps the conductivity in some manner. So these are experiments which can be looked into in the future as well.
Okay. And what was your membrane? You use solid membrane, right? This is the last question.
Yes. Actually, this is not here. It says Nefian membrane. Actually, it was not Nefian. It was AMI. It's an anion exchange membrane that we actually use here.
Okay.
The Nefian membrane was used for the ionic liquid, I think, but it wasn't performing very well. So we chose the anion exchange membrane from AMI, this company called AMI.
Okay. Okay, thank you.
Thank you.
Barun Hocam, there is a question on chat box. One of our participants, Taha Yasin Eken, asked. I want to ask about the CV test. How did you make the connection of carbon felts in 3-electrode system? Did you knit the felts with platinum or use a platinum electrode with a holder as working electrode? Did I pronounce correctly some of terms?
Yes. Yes.
Okay.
So here, I mean, I personally didn't do these 3-electrode experiments. My colleague was doing that in the chemistry department. in Imperial College. However, the way I used to do it during my PhD is I would have a copper connector. It's a copper, not foil. What do you call this? The not even a rod. It's the copper foil. Yes, sorry, copper wire. I would then connect the copper wire to the carbon felt. I would like put it through the carbon felt up to a certain limit. Then I will apply some sort of like a, the nail varnish kind of material, which is resistant to the acid or the particular electrolyte that I'm using. And then I would put acrylic type of what do you call a glue that is also resistant to the acid to hold this, to make the carbon felt connected to the copper wire. And then I would use that as for the cyclic voltammetry. I'm not sure if I could answer the question here.
It thanked you. Is there any question?
One thing I forgot to mention is that before cyclic voltammetry, we let the electrodes rest in the electrolyte solution for 9 hours at least. So that also played a difference in the results.
Thank you, Hocam, for this information. If there's no question, we can finish our webinar for today. Thank you for your presentation, Dr. Barun. Thank you all for your participation. The next Nano Open will be held on April 26th.
Okay.
Thank you and have a great day.
Thank you very much.
Thank you.